Hello and welcome to our Vertical Computer 3. Great job getting through the montage, and now you're here in our completely unscripted tour of the computer. My name is Cold Fusion,
I'm Baron von Satchel.
and this is a project we started, what was it, like 6 months ago?
It depends on what you define as started, because we had the idea to do this like 5 years ago.
Anyway, just to give you a quick overview of the computer, right now we're in the control room, and if I fly up here, you can see the whole computer in all of its glory. And this computer is built entirely of survival-friendly components. So that's redstone and comparators and redstone repeaters mostly. We tried not to use anything that would be difficult to gather in survival mode. So there aren't any pistons, no command blocks, of course.
Yeah, so the reason we call this the Vertical Computer 3 or VC3, it's not actually really the third version. We called it that because it's based on the LC3, the Little Computer 3, which is a 16-bit computer that is used primarily in education. We had to deal with it in a class that we took together on assembly language. And so we have recreated most of the functionality of the LC3 here in our computer and basing it off of that architecture and not trying to invent our own whole cloth is part of how we were able to finish this because it became a challenge of how do we accomplish this thing that we already know what it does instead of how do we make a thing to make a computer.
Yep. All right, before we go on our computer tour, it's really important to understand how this computer encodes data. Now, all the data is encoded in binary. You can see these lamps are labeled with numbers. There's a 1 and a 2 and a 4. All of these are powers of 2. And you can actually encode all the numbers up to 65,535 with all of these different powers of 2. For instance, if this lamp is on, and this lamp is on, and this lamp is on, that means we're encoding a number that's 1 plus 2 plus 4, so 7.
this these levers here um, allow you to input a number in binary, same as those lights which are output. Um, so you have the ones bit. So if I flick 1, 4, 16, number I'm putting in is 16 plus 4 plus 1. That's 21. And then there's various things I can do with that number. So over here, we have write to RAM at PC. So the PC, or the program counter, is where the computer currently is in memory.
Mhm.
You also have write to register. So there are 8 program registers. These are the same design of memory storage as the RAM, but they're faster and easier to access than the RAM. And so that's the sort of intermediate stage for um, where you store data you're immediately working with.
So I get to talk about why these levers are color-coded. And that's because you're not just entering data into your RAM, you're actually entering instructions. Instructions are just binary data that the computer then loads off of the RAM and will interpret. And I'm not going to go into too much detail for each instruction here, just because it's a lot. If you want to check out and try programming this computer for yourself, you can download this world, and there's this user's manual here, which has a lot more detailed information on each instruction and exactly what every single part does. Alright, so now that we've introduced the computer, we're going to fly over here, and we had a little bit of extra room inside the case, so we decided to build a little museum of all the really important components.
Yeah, the computer
So
didn't quite fill the whole rectangular bounding box, so we used this extra space in the corner to build small little demo pieces of all our components. So here, this is 1 bit of RAM. This is you can see the actual RAM for the computer through this black stained glass. But so the way this works is, so see the levers here. This is your input, and this repeater is locked by default. That's where the data is actually stored. So this can go on and off. It doesn't change this repeater. If you're familiar with redstone, you probably know how a repeater lock works. And if you want to set the bit, hit it. Now it's off. It's locked again. Again, that doesn't change. If you want to read the bit, press this. This is a neat little trick, which is this is a comparator in subtract mode, repeater going in the side. So even when this is on, sending a maximum strength redstone signal into the back of this comparator, it is subtracted, or it has another full strength redstone signal subtracted from it, and the resulting signal is 0.
Mm-hmm.
So as long as this repeater is being powered and sending power into the comparator will output nothing. And that's how we determine which address that we're reading from. So you select the address you want to read from, unpower that repeater, and it lets the data through.
Having data storage is nice and all, but it's not very useful if you can't actually do anything with it. So this right here, this is a cross-section of our ALU, or arithmetic logic unit. And this is a 3-function ALU. This is 2 bits of it, 2 layers of it. And we have 3 different operations. We have not, we have and we have add.
So over here, we have our 2 inputs. So each of these is a 2-bit number. So that can be 0 to 3. Right now, they're both on 0. So if we wanted to make input 1, 1, turn that lever on. So now, not input 1 is 2 because it inverts each bit. So the bit that is 1 is off, and the bit that is 0, the 2's bit, turns on. So that's not input 1, and turns on the output bit if input bits at the same place value are both 1. Then finally, we have add. So this is input 1 plus input 2, sort of the one that makes the most sense to people who aren't familiar with computers. This is just addition. So 1 plus 1 is 2. This is binary, so the 2 1s will leave a 0 in the 1's bit and carry up to the 2's bit. If we then turn on a 2, 1 plus 1 in input 2 makes 4. The reason we call this the vertical computer is because everything is vertical. So the bits are stacked vertically. So the 1's bit here is at the bottom, and then the 2's bit. And then if we stacked more, up to the sky limit, you could have as many bits as you wanted.
Yep. And one of the biggest challenges of creating this computer was creating computer components that match the vertical bits, because a lot of Minecraft computers are built horizontally. We had to sort of reinvent different components. Yep, and he gets all the credit for coming up with all this crazy stuff.
You found this. This is a XOR exclusive OR gate.
I found it on the wiki. I didn't invent it.
Yeah, well, still, you found it.
It was a team effort. He invented stuff, and I found stuff on the wiki. All right. Yeah. Right. So we have a couple more components to show off.
This is another one of my designs, the vertical bus crossover. So a bus in computing is just a bunch of wires or connections in parallel that each have 1 bit of data. And what this does is this allows vertical um, buses of data to pass through each other without interference. And so this is a big innovation that allowed us to get the dimensions of the computer down as small as they are, because the lines don't have to like awkwardly spread out to interweave or navigate around each other or go way up into the air to jump over the top of each other. They can just pass straight through with no additional horizontal profile. So yeah, so you can see the blue lines connect, the yellow lines connect, neither one interferes with the other.
Okay, now we have one last component to show here, which is what we call the torch slicer. And this also isn't something particularly like fancy or flashy, but it is really important. It is an important piece of our computer, so we wanted to show it off here in the museum. Essentially, when this lever is off, it won't let any data through to these output buses. So if I flick these levers, it doesn't matter. It doesn't turn on any of these lights. However, if I flick this lever, it unslices because it's no longer powering these torches. Boop, and it will let the data through. So this is really important for letting data in and out of specific areas in our computer. Alright, now that we've explained everything over in this part of the computer, we can finally show off the redstone!
Now that,
Yay!
now that we've
So,
seen the micro versions of everything, we can show the real thing in action.
yep. So if we go up that water column, we can fly around here, and this is the whole computer. Now we have a few different components here, and they're all labeled by yours truly with beautiful, gorgeous banners. This right here is the RAM. Lots and lots of stacks of those same components that we showed off earlier. Over here are registers, which has this pretty much the same design as the RAM. Whoa, a little bit of
It's
lag
the same
spike.
design as the RAM, but you select them differently, and there's fewer of them, so it's faster
Yep,
to
and
interact
going
with
over the
them.
RAM always lags my computer. Over here we have the ALU, and this is just a bigger, it's just 16 tall stack of that same component that we showed you earlier. Down here, this down here is the address adder and the PC. Essentially what the address adder is all about is sometimes we want to add an offset to a RAM location. Like let's say we have RAM location 32 stored somewhere, but we want to go like 2 further than that. We can go to 34. There's lots of different uses for it, and it helps. That's another thing that has made this computer so compact, is just having a dedicated address adder. And this is the same thing as the ALU, just 6 tall instead of 16 bits tall.
At the end of an instruction, when the program is not frozen, it will take the current PC, current location in memory, and add 1 using this adder. So if you're at location 17, you add 1, it becomes 18. Then it
Hmm.
stores it back in the PC, and that's how you move through the program, selecting instructions in sequence and running the code in order. And then you have instructions such as branch and jump to navigate around and not do instructions in order. If, for example, you want to have conditional statements or skip over lines of code.
Hmm. And that's
Um,
what all of this tangled mess is all about. This is just all the different timing circuits for each of the commands interacting with this control bus that will do different things on the computer. Like some of these control buses might say, hey, we want to write to a register. Or one of them might say, hey, let a register address down through one of these spindly orange lines.
you think of it like an orchestra. This is the conductor conducting all of the different instruments of the computer.
Now, and that's it. You fully understand this computer, right? Well, why don't we go ahead and let's fly over here and let's just pretend we're an instruction. And that might help you better understand how this thing is actually working. So let's say I Cold Fusion, I am an add instruction. So I'm going down, coming out of the RAM from one of these different locations. It's going to go through all of these different circuits here. Do you want to explain what all of this mess is?
These here are decoders. So basically, these these four bits here. The top one is we call it the go button. That's basically the signal that once everything has loaded up and stabilized, triggers it to actually run the instruction.
Hmm.
But the four immediately below that are the bits that tell the computer what instruction we're actually running. And each of these decoders here um, is essentially listening for a different combination of those four bits, a unique combination that corresponds to that instruction. And what that does is if we're an add command that's 0001, conveniently, our program is on an add command right now,
Yep.
then all of these are going to be off because it's not their code. But here in add, it was on just a second ago. Um, Over here in add, if it's 0001, then this decoder, all of these will um, change to allow this torch to come on.
Yep. Okay, so let's say I'm an add command. Specifically, I'm an add command that says we're going to add 1 to whatever is in register 0 and place it back into register 0. What would happen here?
So the first thing is because we are doing a fixed number 1, not another register, it would take a path that corresponds to a fixed number, which the fixed number will be on this instruction bus. It will come through these pink lines here. We will open the gates for it to come these red lines, sneak around the back, go over here into input 1
Hmm.
of the ALU. As you can see, it's only 5 bits because the instruction bus is limited to 16 bits and we need the other bits for other parts of the instruction.
Yep. And then once that signal gets here, after a little short delay, it will unlock this repeater, and this is the first input in our ALU. Okay, so what happens next then?
Then we go down a layer. This timing circuit is organized into 3 vertical layers.
You can't really tell very much though, because it's all just, there's just
It's
staircases
pretty
everywhere.
dense. But the next thing it does, now this is the common step that's the same whether you're doing an add and or not, and it's the same whether you do a register plus register or register plus a fixed number. This loads will load the data from our 0 source register, and it will allow the data to flow from this incoming side of the data bus, which will then get locked into this repeater,
Oh,
which is
like it just
input
did,
2.
like it just did right there. It looks like it just locked in a number. Yeah.
Yep.
So what happens, so it has both of its inputs. It's calculated its add, whatever was an R0, and it's added 1 to it. What happens then?
Well, then go down to the final layer of this sort of layered, but not really timing circuit. After a long delay to make sure that we've given it time to potentially ripple carry, it then sends a signal one of our slicers that we talked about. There are 3 of them, one for each operation. Because we're doing an add, conveniently, it just happened. This vertical redstone tower would become unpowered, which would allow these torches to come on and send a signal here through the vertical crossover and onto the outgoing side of the data bus,
Whee!
which then flows this way through
Right.
the RAM and all the way around and back to our registers. And then once we've given that data time to get all the way to the registers, specifically R0, because that's what our command was doing, once it's gotten here, it will quickly send a pulse on the read-write control for the RAM, which will unlock this repeater and quickly lock it again, which will clear whatever data was in it before and um, lock in the result of
Like it,
our addition.
like it just did.
How
Look at that.
convenient.
So there's one other really important function on this computer, which is this section right here, this whole NZP section. This is for conditional branches. So if we do an add command or anything that stores data in a register, it will store in these redstone lines, in these repeaters right here, whether or not that number that was stored was negative, 0, or positive. And one of these redstone lines will always be on because it's either a negative number, 0, or a positive number. So right now, this P is what's selected. That means whatever it was that we last stored in a register was a positive number. And these little flags here are used for our branch command, which we can use to, if one of those things was true, you can program it to go jump to a different line to read next in memory. Yep, and that's a computer. Just running one instruction at a time. Each instruction does something different. There you go. Right now, we're running a program that calculates prime numbers. And you can see if I go to location 0 here, you see all these lamps are on. This is actually a program instruction that we've loaded at some point. We can actually see what line are we on right now. We're on line 17, so whatever is in 17.
No, we just moved to 18.
Oh, we just moved to 18. Well, we're running these lines of code right now. What it's doing is it's filling locations 20 all the way up to location 63 with prime numbers. So we can take a look in location 20, and we have a 3 in that location. Now we've skipped 2 just because we want to make the primes program as short as possible. So we're only doing odd numbers.
We're doing odd numbers starting with 3.
Yeah. You can see in memory location 21, we have the number 5. This is a 1 plus 4. In this one, we have 7. We have a 1 plus 2 plus 4. And then we have this is not a 9, but this is an 11. 1 plus 2 plus 8.
This is because our program would have checked the number 9, found it to be an even multiple of 3, one of our previously discovered primes. And because we know that it's an even multiple of something, it's not a prime, so we immediately throw it out. It would then move on to 11, and then check all of the previously discovered primes, find that it isn't a multiple of any of them, and save 11 as the next prime number. And it will just continue doing that, and it has continued doing that for many hours.
Yep.
Until it has filled up all the remaining 44 addresses.
Yeah, so it looks like it's gotten up to memory location 37 now. That's what number is
I think
that?
that's a 67.
That's a 67.
Yeah, because
And
this
it looks
is
like it's working on memory location 38, it's trying to figure out what the next prime number is after 67.
All right, and that's the whole computer. So we've tried to explain everything in simple enough terms that even if you're not a computer science student, you'll be able to mostly understand, at least individually, what each part does and maybe how they can work together in concert to run a program.
Hmm.
Um, so hopefully you enjoyed it. We're quite proud of our creation, especially since we've never seen a computer um, quite like this before.
Hmm.
Um, this vertically stacked bits design that I think allowed us to save a lot of the horizontal space over a lot of other um, Minecraft computers, especially 16-bit Minecraft computers,
Yeah, and making
which
this thing
tend to be.
was quite an ordeal, but it wasn't nearly as insurmountable as I thought it would be. I definitely recommend for those of you watching at home, go ahead and try making your own computer. It doesn't have to be as complicated as this one. It can be relatively simple, but it's once you get the key components down, it's not impossible.
I mean, yeah, like I agree. We didn't think that we'd ever finish this, but all we did is take it piece by piece.
All right, well, you've made it to the end of the video. Congratulations. Good job sitting through all that. Now you're thinking with redstone. TM. Thank you so much for watching, and I hope you learned something about computer science and enjoyed watching this video. Don't forget to, I don't actually care if you like or subscribe. It doesn't matter to me. But I hope you have a wonderful day, and we'll see you another time.
Check out his Minecraft maps that he makes.
Available on the
I would tell
marketplace.
you to check out my Minecraft mods, but I haven't updated one of them since I was in high school.
Yep.
Um, so
Later, nerds.